Okay, apparently we are short of a herald, so I'll just step in. Let me introduce you to Travis Goodspeed, who is a very interesting and resourceful MSP430 hacker. And he will show you how to start embedded development with very few financial with very few money, and hopefully that will be very interesting, and you can start doing your own embedded development right after this talk.
Howdy. So in this lecture, I'm going to show you how to take apart a $20 Introduction to Microcontrollers kit from Texas Instruments and rewrite the software not of the target board that you're supposed to program, but of the programmer itself. So in doing that, you have to copy out the existing software and reverse engineer it sufficiently to understand what has to be in the replacement. So to quickly review, the MSP430 is a 16-bit microcontroller. It's von Neumann architecture, and it has a table of interrupts at the end. So wherever you have like a callback from hardware or an event that's fired when, say, a pin rises or a byte comes in over a serial port, the microcontroller just looks at an address at the end of memory and pushes it into the program counter. I did a hack of the bootloader of this chip, allowing its password protection to be bypassed. And in this case, they actually wrote their own bootloader on top of that. So in addition to the bootloader that's in permanent master ROM, there's also one in flash memory. So when I say bootloader in this lecture, I'm not referring to the same thing as I did in my day one lecture. And also, a microcontroller doesn't have a real operating system in it. So instead, you have individual memory mapped addresses that you write to affect the outside world. So you can change pull up and pull down resistors on an I/O pin. You can change that pin from an input to an output. You can pull it high, pull it low. And there are also clocks and timers and such that you can access by peeking and poking individual addresses. And when you do this, you're not calling a function that exists elsewhere within the chip. You're just writing to an address, waiting a bit, and then reading from another address, or waiting for an interrupt to fire. This is the device that we'll be hacking. The piece on the left is the target board. It's about the size of 1 euro cent, and it has the MSP430F 2012 or 13 on it. There's also an LED and the pull-up resistor and the decoupling capacitor and all of everything you need to have a functional device. But it's small, and it doesn't have much power. It only has one serial port. It can only do so much. And while it's fun to play around with, I'd rather have an advanced project out of this. And I'd rather have a reverse engineering project out of it. So I took the right side of this, which is a JTAG in-circuit debugger, and I dumped its firmware. And I reverse engineered it, as well as the USB to serial section of the board, which behaves differently. Another target board that you can have, the intended route for you to move up with TI, is this. It's a 2.4 gigahertz wireless sensor node, powered by the same connector and running firmware that they supply for you. Now, on the EZ430, if you read the documentation, you'll find the JTAG pins, and they exist as test points on the side of the device. So if you build an adapter, you plug it up, you can then hook up another in-circuit debugger from TI, and you can dump all of the code from the target device. You can also replace the code. And the initial motivation for dumping this was to gain Linux support on the radio version of the board, which is Red. Its firmware is incompatible with Linux. And you can either run it through VMware, which isn't terribly reliable, or you can copy the firmware from the blue board into it. And you do this with GDB. So you just load up GDB connecting to the target, and then you say dump memory, IHEX, and then the file name and the address range. You start at 200 and you go to 1000 hex because everything beneath 200 is I/O. And if you read or write I/O, you cause unintended side effects elsewhere in the system. So reading from it isn't terribly damaging, but if you were to dump all of memory and then write it back into another device, you would change the clocks and you would actually break the JTAG session. The schematic diagrams for this are freely published by TI in an application note, SLAU 227. They're all unique words, so if you Google for that, you find no other document. They don't present well on stage, and I suppose there aren't handouts here. But if you have the slides, you can look at this diagram. And it comes in multiple pages. So here we have the MSP430 along with the programming port, J2 on the right. It's here. You have series resistors and all of that stuff. And then there's a USB to serial chip, the TUSB3410, which is similar to the FTDI chip, many of you will be familiar with. And there's a serial EEPROM, the CAT24FC16UI. Sometimes that part number varies. It'll be a larger EEPROM. But the idea is that firmware for this device resides entirely within the MSP430, which is the CPU of the device, and also within the CAT24 EEPROM, which provides firmware for the TUSB3410, which is a USB to serial chip, and it's also a CPU. It has an embedded 8051 core, and the reason why the red version of this board won't work in Linux is that instead of using the native USB to serial mode of this chip, TI wanted an extra serial port. So they wrote custom 8051 code and then matching software on the PC end to allow them to have 2 serial ports from a chip that in hardware is only supposed to give 1. So these are the 3 main chips of the board. You've got the MSP430, the CPU. You also have the TUSB3410, which is a USB to serial chip and also a CPU. And then you have the CAT24C32, which is an EEPROM and contains the code for the 3410. In hardware, they're connected like this. You have a single I to C bus between all 3 of the chips, and then a UART that only runs from the 430 to the TUSB. So to dump the code, I took 2 hypodermic syringes running to an I2C adapter. And the nice thing about I2C is that it's multi-master. So when I plug these syringes into the board, and I've got the board plugged into the USB port, I can actually dump the code of this chip on the same bus that's being used by the actual chip in operation, and there are no collisions, there are no errors. I get a clean dump of the chip, and the operating system doesn't throw any errors or complain. So in the classic version, the EZ430F 2012, there's nothing interesting inside of the EEPROM. It says Texas Instruments and Unicode, and it has the basic configuration requirements for the USB to serial mode of the target chip. In the EZ430 RF2500, the Zigbee version, it actually contains executable code, and it prohibits updates over the USB port. So not only can your computer not only can your Linux machine not speak to it and get a serial port, but it can't instruct the chip to use the firmware that it has within the Linux kernel, the binary blob. And they do this to provide the 2 UARTs. The hard one goes to the onboard MSP430. This is how your computer talks to the debugger. And there's also a soft one to the target board so that when you have the Zigbee node plugged in, you can send commands to it. You can say, transmit this packet or send me packets. The soft UART is horribly unreliable. So if you intend to use this in a commercial application, be sure to construct a line-level serial port, such as out of a TUSB chip. an FTDI chip. So I dumped the firmware of the MSP430 and I ran it through an analysis tool that I've built called MSP430 Static. Firmware analysis tools, or I suppose it's not firmware in the 32-bit range. So on a PC, you have IDA Pro. And IDA Pro uses lots of very sophisticated algorithms to search in anything approaching a reasonable amount of time. On this chip, all of memory is 64 kilobytes. 32,000 instructions is the absolute maximum. And so you don't need these advanced, fast algorithms that make IDA Pro possible. You can just throw everything into an SQL table and do queries on it. So in 2 days, I wrote this analysis system in Perl. And this whole graph is done by a couple of SQL queries. Everything in red is a number other than 0 or -1. Everything in white is a 0. You'll note that RAM is zeroed out toward the bottom because that's what RAM does when it's reset. Flash memory resets to 1s. So you reset the entire sector to 1s, and then to write a byte to it, you move individual bits from a 1 to a 0. So all of the flash memory at the top that hasn't been initialized is in black. It's a bit hard to see, but at the top right, there's a bar of green, and that's the interrupt vector table. And then at the top right of the black region beneath it, there's a line of blue. We'll get to that in a minute, but note that it's exactly where the green bar is, just a little bit lower. And then I can draw a call graph. I can instruct it to dump a graph theory directed graph of every parent and child function. And you'll note that the spaghetti on the left is connected. There's no function that isn't reachable from somewhere. So it's all tied into one large structure. While on the right, everything is also connected, but it's a lot smaller, and it's not connected to the left region. And the reason for this is that you have two programs in this chip. So this thin band of red at the top is the structure on the right, and the lower region is the mess on the left. And then to zoom in on the interrupts table, you have the green interrupt vector table at the very top. That's 0x FFE0 to 1,000 hex, 10,000 hexes. And then beneath that, you've got the blue region, which is for proxying interrupts. It's a second interrupt vector table for the lower unit that's not implemented in hardware, but is instead implemented by proxying functions. So at the bottom right here, we have the IVT as a circle, and then all of its handlers come out from it. And those will handle things such as an incoming serial byte. And you'll note that only one of them actually calls another function. And that is too small to read, but that's init. Okay, so then init calls main, which calls configure, and these names had to be written by hand after the code was reverse engineered. But only one of the interrupts actually calls anything, and that is the interrupt that is executed when the chip is turned on. And then this code here is used to fetch serial bytes. You've got get byte, which is called many times from the get command function. Put byte is when bytes are written over the serial port, and this is for a sort of wake-up initialization with the PC. So when you start GDB proxy, so that you can debug the target board, before the actual JTAG debugger software is run, this code is run, and it's here that updates are read into the device. So it quickly checks over the serial port to see if there's new firmware, and if there is, you can load it through. To identify functions, you can't use symbols because they don't exist inside of the chip. If you were on a PC, you would have DLLs with indexes. You might have debugging symbols left in by the author. None of that stuff exists within the chip itself. And doing it by hand is too slow for the large number of functions in the smaller image. On the upper one, it's small enough that you can go through by hand and find each one and read it. I also have support for software